Okay, well, welcome back to College Physics 1. We're continuing on in our coursework here, and this slight correction that unfortunately I had these parts in the wrong location, and so the section on mechanics goes all the way up to topic number 9, so I apologize for that error. And so we're now going to be covering topic number 8 today, which is rotation, equilibrium, and dynamics. So just keep that in mind. The previous 7 lectures were referring to a quote shorter section for mechanics, and so we have a couple more things that will be related to that area. So let's just focus a minute here on this interesting picture. It's in our textbook as well. So this is a large balanced rock on the Garden of Gods in Colorado Springs, Colorado. And although it seems a little bit strange, it is in mechanical equilibrium, although it wouldn't take much, relatively speaking, to disturb that rock. But at least at this point of view and time, including the fact that people were walking around it, it is in equilibrium. Okay, we're going to go over the reading questions as we normally do, relatively quick fashion. We'll go over the main course material, and there'll be some questions as we engage with that, and then finally we'll have a summary. And so have maybe about half a dozen questions here. So which of the following screwdrivers would likely be the most effective to loosen a stubborn screw? Assume that the size of the driver head is the same in each case. So we have different type of scenarios with the length of the handle and how wide it is. And so here we see with a handle that is 8 centimeters long and 4 centimeters wide. So is what they were postulating. So you get the best ability to loosen the screw under that condition. A ball rolls without slipping down an incline A, starting from rest at the same time a box starting from rest and slides down incline B, which is identical to incline A, except it is frictionless, which has a larger translational speed at the bottom of the ramp. And the answer is the box. Okay. Maybe that's obvious if you think about it. So complete the following sentence. The moment of inertia of an object is it's a function of the axis about which the object is spun. So just to review for that part, and for a skater rotates quickly on the ice, he pushes his arms out. What happens to his angular speed? And it decreases. And I'm sure you've seen ice skaters do this with different tricks that they literally, by putting their arms in, they start to go faster. They pull their arms out and they go slower. And so they can have an interesting effect just by moving their arms. Someone hits a tether ball to make it spin around a pole. The cord then attaches the tether ball to the center pole, then winds around the pole. What happens to the angular speed if the tether ball during the process? And similar to the last question, it increases because it gets closer and closer to the pole, just like when a skater pulls his or her arms in. The center of gravity is a useful point at which to balance an object. For instance, a ruler can be balanced by placing the center on your finger. Is it possible for the center of gravity of an object to be located at the point where no material exists to balance the object? And the answer to that question is yes, it is possible. So let's move on to our topic discussions here. When we learned about linear motion, the objects were treated as point particles, and it didn't matter where the force was applied on the object. But the reality is the point of application does matter. we can use the concept of rotational dynamics and rotational equilibrium to study extended systems. These concepts are important in disciplines as diverse as architecture and biology. Architecture needs to understand the forces that act on buildings, and biologists should understand the forces that work in muscles and bones and joints. So we're getting a little bit of perspective into kinesiology for those that are interested in that, in the folks taking this class. In our studies, we find that an object remains in a state of uniform rotational motion unless acted on by a net torque. That principle is the equivalent of Newton's first law. Also, the angular acceleration of an object is proportional to the net torque acting on it, which is the analog of Newton's second law. A net torque acting on an object causes a change in its rotational energy. Finally, torques applied to an object through a given time interval can change the object's angular momentum. In the absence of external torques, angular momentum is conserved, a property that explains some of the mysterious and formidable properties of pulsars, remnant of supernovas, explosions that rotate at equatorial speeds approaching that of light. So a little bit of a perspective on what we're going to be talking about. So here we have a bird's eye view of a door hinged at O with a force applied perpendicular to the door. So I'm sure you're quite familiar with this with doors in your home or wherever. You already know that forces cause accelerations. Torques cause angular accelerations. Take a look at the figure, which is in an overhead view of a door hinged at point O. Imagine that the door is free to rotate around an axis perpendicular to the slide and passing through O. If a force F is applied to the door, there are three factors that determine the effectiveness of the force in opening the door: the magnitude of the force, the position of the application of the force, and the angle at which it is applied. We will only be dealing with position and force vectors lying in a plane. When the applied force is perpendicular to the outer edge of the door, as it is in the figure, the door rotates counterclockwise with constant angular acceleration. Now let's think about what happens when the same perpendicular force is applied at a point near the hinge. The result is a smaller angular momentum. In general, a larger radial distance r between the applied force and the axis of rotation results in a larger angular acceleration. Also, a larger applied force will result in a larger angular acceleration. Let's look at a special case of forces perpendicular to the position vectors as in the figure. Let F be a force acting on an object and let R be a position vector from a chosen point O at the point of application of the force, with F perpendicular to R. The magnitude of the torque tau exerted by the force F is given by the equation shown, where R is a length of the position vector and F is the magnitude of the force. So here we have a figure as the force is applied farther along the wrench, the magnitude of the torque increases. And so this is one of the reasons why you can have torque wrenches or regular wrenches have various lengths of the tool in order to give you more torque. So this figure illustrates the point of force's application affects the magnitude of the torque. When the force is applied farther out along the wrench in this figure, the magnitude of the torque increases. The torque is perpendicular to this plane. The point O is usually chosen to coincide with the axis the object is rotating around. For example, the hinge of a door or hub of a merry-go-round. Of course, other choices are possible as well. We consider only forces acting in the plane perpendicular to the axis of rotation. So for example, we don't include a force with upward component on a merry-go-round railing, which can't affect the merry-go-round's rotation. Under these conditions, an object can rotate around the chosen axis in one of the two directions. By convention, counterclockwise is taken to be the positive direction, clockwise a negative direction. When an applied force causes an object to rotate counterclockwise, the torque on the object is positive. When the force causes the object to rotate clockwise, the torque on the object is negative. When two or more torques act on an object at rest, the torques are added. If the net torque isn't zero, the object starts rotating at an increasing rate. If the net torque is zero, the object's rate of rotation doesn't change. These conditions should seem familiar to you from Newton's first law. In fact, we have a rotational axis to the first law. The rate of rotation of an object doesn't change unless the object is acted on by a net torque. So in this figure, we have in A, a force F acting at an angle theta equals 0, exerts 0 torque about the pivot O. In B, the part of the torque perpendicular to the door F sine theta exerts torque F sine theta about O, and C, an alternative interpretation of torque, is given in terms of a lever arm of D equals R sine theta. So sometimes the applied force is not at right angles to the position vector. Imagine that a force exerted on a door is directed away from the axis, as in the top figure, say by someone grasping the door knob and pushing to the right. Exerting the force in this direction couldn't possibly open the door. But if the applied force acts at an angle to the door, as in the middle figure, the component of the force perpendicular to the door will cause it to rotate. The bottom figure shows that the component of the force perpendicular to the door is F sine theta, where theta is the angle between the position vector R and the force. When the force is directed away from the axis, theta equals 0 degrees. That is sine 0 degrees equals 0, and F sine 0 degrees equals 0. When the force is directed towards the angle, theta equals 180 degrees, and F sine of 180 degrees is 0. The maximum absolute value of F sine theta occurs when F is perpendicular to R, that is when theta equals 90 degrees or theta equals 270 degrees. Let's put these ideas together for a moment in a general definition of torque. When F is a force acting on the object, R is a position vector from a chosen point O to the point of application of the force, and theta, the angle between R and F. Again, the vectors R and F lie in a plane, and for our purposes, the chosen point O will usually correspond to an axis of rotation perpendicular to the plane. So in this figure, as the angle between the position vectors and force vectors increases in part A and B, the torque exerted by the wrench increases. So this figure illustrates how the magnitude of the torque exerted by a wrench increases as the angle between the position vector and the force vector increases at 90 degrees, where the torque is a maximum. A second way of understanding the sine theta factor is to associate it with the magnitude R of the position vector R. The quantity D equals R sine theta is called the lever arm, which is the perpendicular distance from the axis of rotation to a line drawn along the direction of force. The value of tau depends on the chosen axis of rotation. Torques can be computed along any axis regardless of whether there is some actual physical rotation axis present. Once you choose your point, you must use it consistently throughout a given problem. So in this figure, we can use the right-hand rule. Point the fingers of your right hand along R and curl them in the direction of F. Your thumb then points in the direction of the torque out of the page in this case. Note that either theta or theta prime can be used in the definition of torque. So torque is a vector perpendicular to the plane determined by the position and force vectors as illustrated in the figure. The right-hand rule determines the direction can be determined by the right-hand rule. So just to reflect this again, you point the fingers of your right hand in the direction of R, you curl your fingers towards the direction vector F, and your thumb then points approximately in the direction of the torque. So in this case, it's coming out of the screen. Notice that there are two choices of angle in the figure. The angle theta is actually is the actual angle between the direction of the two vectors. The angle theta phi is literally between, quote, the two vectors. So which angle is correct? Because sine theta equals sine 100 degrees minus theta, and sine 180 degrees times cosine theta minus sine theta cosine of 100 degrees is equal to 0 minus sine theta times minus 1 equals sine theta. Either angle is correct. So we're fortunate that the math just comes out in this situation. So the problem we will be dealing with in this course are objects rotating around an axis perpendicular to the plane containing R and F. So if these vectors are in the plane of the slide, the torque will always point either into or out of the slide parallel to the axis of rotation. If your right thumb is pointing in the direction of torque, your fingers curl naturally in the direction of rotation that the torque would produce on an object at rest. So in this figure, the net gravitational torque on an object is 0 if computed around the center of gravity. The object will balance if supported at that point or any other point along a vertical line above or below that point. So the figure shows an arbitrary shaped object in the XY plane. The object is divided into a large number of very small particles weighing m1g, m2g, m3g, etc. Having coordinates shown, if the object is free to rotate around the origin, each particle contributes a torque about the origin that is equal to its maximum, its weight multiplied by the lever arm. For example, the torque due to the maximum weight m1g is m1g x1. Our goal here is to find the point of application of the single force of magnitude W, where m is the total weight of the object. This is the point where the effect of the rotation of the object is the same as that of the individual particles. This is called the object's center of gravity, something that can be quite useful for simplifying problems if you can think about and locate that center of gravity and think of it as a point source then. So let's equate the torque exerted by W at the center of gravity to sum all of the torques acting on the individual particles. We assume that G is the same everywhere in the object. Then the G factors cancel. Here, X of CG is the X coordinate of the center of gravity. The same can be done for the Y coordinate and Z coordinate of the center of gravity. These three equations are identical to the equations for the similar concept called center of mass. The center of mass and the center of gravity of an objects are exactly the same when G doesn't vary significantly over the objects, as will be the case with all the problems we will encounter in this course. So we will use the concept of center of gravity and center of mass interchangeably. So here in the figure, we have an experimental technique for determining the center of mass of a wrench. And so sometimes it is possible to guess a location of center of mass. The center of mass of a homogeneous symmetric body must lie at the axis of symmetry. For example, the center of mass for a homogeneous rod lies midway between the ends of the rod, and the center of mass of a homogeneous sphere or a homogeneous cube lies at the geometric center of the object. The center of mass of an irregularly shaped object, such as a wrench, can be determined experimentally by suspending the wrench from two different arbitrary points as shown in the figure. The wrench is first hung from point A, and a vertical line AB, which can be established from the plumb bob, is drawn where the wrench is in equilibrium. The wrench is then hung from point C, and the second vertical line CD is drawn. The center of mass coincides with the intersection of these two lines. In fact, if the wrench is hung freely from any point, the center of mass always lies straight below the point of support. So the vertical line through that point must pass through the center of mass. A rigid object in a uniform gravitational field can be balanced by a single force equal in magnitude to the weight of the object as long as the force is directed upward through the object's center of mass. We can apply Newton's second law to a system that the total mass m asymptote times the acceleration of the center of mass equals the sum of the forces, where the sum of F external is external forces acting on the system, and F internal includes all the internal forces acting on the system. All internal forces come as action-reaction pairs, and because the vectors in these pairs have equal magnitude in opposite directions, they cancel out. So the second law for the center of mass may be written without internal forces. In both one and two dimensions, our equations are exactly the same as for a single particles. The two-dimensional equations can be written simultaneously. So an object in mechanical equilibrium must satisfy two conditions. The net forces must be zero, the external forces, and the next external torque must be zero. So the first condition is a statement of translational equilibrium. That is, the sum of all forces acting on the object must be zero, so the object has no translational acceleration, or A equals zero. And the second condition is a statement of rotational equilibrium. The sum of all torques on the object must be zero, so the object has no angular acceleration, thus alpha equals zero. For an object to be in equilibrium, it must move through space at a constant speed and rotate at a constant angular speed. So let's talk about a problem-solving strategy for objects in equilibrium. Because we can choose any location for calculating torques, it is usually best to select an axis that it makes it at least one torque equal to zero, just to simplify the net torque equation. Here is a general procedure for solving problems that involve objects in equilibrium. So number one, as usual, you want to diagram the system, including the coordinates, and consider a convenient rotation axis for computing the net torque on an object. Number two, you want to draw a force diagram of the objects of interest, showing all external forces acting on it. For systems with more than one object, draw a separate diagram for each object. Most problems will have a single object of interest. Number three, apply the second condition of equilibrium. This condition yields a single equation for each object of interest. If the axis of rotation has been carefully chosen, the equation often has only one unknown and can be solved immediately. So number four, apply the first condition of equilibrium. This yields two more equations per object of interest. And number five, solve the system of equations for each object of the two conditions of equilibrium yield three equations, so usually with three unknowns, and thus we can solve by substitution. So let's talk about the rotational second law of motion. So an object of mass m attached to a light rod of length r moves in a circular path on a frictionless horizontal surface while a tangential force F sub t acts on it. The acceleration and torque vectors are perpendicular to both the radial and the force vectors. When a rigid object is subject to torque, it undergoes an angular acceleration that is directly proportional to the net torque. This is analogous to Newton's second law. Well, we can derive this result. So the figure shows a system consisting of an object of mass m connected to a very light rod of length r. The rod is pivoted at the point O, and its movement is confined to rotation on a frictionless horizontal table. Assume that a force F sub t acts perpendicular to the rod, and so is tangent to the circular path of the object. Because there is no force to oppose this tangential force, the object undergoes a tangential acceleration a sub t in accordance with Newton's second law. So we can multiply both sides of this equation by r. substitute the equation relating tangential and angular acceleration into our expression. The left side of this equation is the torque acting on the object about its angular axis of rotation, so we can rewrite it. This results that shows that the torque on the object is proportional to the angular acceleration of the object, where the constant of proportionality mr squared is called the momentum of inertia of the object of mass m. Notice that because the rod is very light, its moment of inertia can be neglected. So as we discussed, torque tau is a vector perpendicular to a radial vector r and a force vector f. The angular acceleration points in the same direction as a torque, as you can see in the figure. A force exerted clockwise yields a negative torque, and a force exerted counterclockwise results in a positive torque. In a similar way, the angular velocity vector points in either the same direction as alpha or in the opposite direction. So let's talk about this a little bit and have a question here. So using a screwdriver, you can try to remove a screw from a piece of furniture, but can't get it to turn. To increase the chances of success, you should use a screwdriver that is, and the answer is, has a wider handle. And so a larger torque is needed to turn the screw. Increasing the radius of the screwdriver handle provides a greater lever arm and hence an increased torque. And maybe you've seen some screwdriver sets that has something you can put on top of the normal handle that can actually make the handle a little bit wider, and thus you can get more torque. So let's talk about torque on a rotating object. So in the figure, in the top, we have a solid disk rotating around its axis, and the one below, the disk consists of many particles, all with the same angular acceleration, is what they're trying to let us think about. So let's consider a solid disk rotating about its axis, shown in the top figure. The disk consists of many particles at various distances from the axis of rotation. And this is shown in a little bit more detail in the bottom figure. The torque on each one of these particles is given by our torque equation. The net torque on the disk is given by the sum of the individual torques on all the particles. Because the disk is rigid, all the particles have the same angular acceleration, so alpha is not involved in the sum. From the bottom figure, we can write the equation shown here. The quantity is a momentum of inertia I of the whole body. Using this, we see that the net torque on a rigid body rotating about a fixed axis is given by this equation, which says that the angular acceleration of an extended rigid body is proportional to the net torque acting upon it. This equation is a rotational analog of Newton's second law of motion, which, with torque replacing force, moment of inertia replacing mass, and angular acceleration replacing linear acceleration. The moment of inertia in an object is related to its mass, but there is an important difference between them. The mass m depends only on the quantity of matter in an object, whereas the moment of inertia I depends on both the quantity of matter and its distribution in the rigid object. So here's a question for us to consider is, a constant net torque is applied to an object. Which one of the following will not be constant? And the answer is angular velocity. And the reasoning is, since the object has a constant net torque acting on it, it will experience a constant angular acceleration. Thus, the angular velocity will change at a constant rate. Here's another question. Two rigid bodies shown in the figure have the same mass, radius, and angular speed. If the same braking torque is applied to each, which takes longer to stop? And the answer in this case would be B. The hollow cylinder has a larger momentum of inertia, so it will be given the smaller angular acceleration and take longer to stop. So here's a figure from the textbook, the drive wheel and gears of a bicycle. If we look at the figure of a 5-speed gear system, where the drive change can be adjusted to wrap around any of the 5 gears attached to the black wheel, the gears with different radii are concentric with the wheel hub. When the cyclist begins pedaling from rest, the chain is attached to the largest gear because it has the largest radius. This gear provides the largest torque to the drive wheel. A large torque is required initially because the bicycle starts from at rest. The bicycle rolls fast. As the bicycle rolls faster, the tangential speed of the chain increases, eventually becoming too fast for the cyclist to maintain by pushing the pedals. The chain is then moved to a gear that is smaller radii, so the chain has a smaller tangential speed that the cyclist can more easily maintain. The gear doesn't provide as much torque as the first, but the cyclist needs to accelerate only to a somewhat higher speed. This process continues as the bicycle moves faster and faster, and the cyclist shifts through all 5 gears. The 5th gear supplies the lowest torque, but now the main function of that torque is to counter the frictional torque from the rolling tires, which tends to reduce the speed of the bike. Thus, the small radii of the 5th gear allows the cyclist to keep up with the chain's movement by pushing the pedals. And I'm sure you've had experiences. This is more thinking in terms of a flat surface. If you're on a hill, you may want to go to the larger wheels so that you can keep going. So in this figure, we're talking a little bit more of the moment of inertia. And so the baton of length 2 and mass 2m, the moment of inertia about the axis through the baton center and perpendicular to its length is 2 ml squared. So have we seen a small object of a particle has a moment of inertia equal to mr squared about some axis. The moment of inertia of a composite object about some axis is just the sum of the moments of inertia of the object's components. For example, let's suppose that we have an individual that twirls a baton as in the figure. And we assume that the baton can be modeled as a very light rod of length 2L with a heavy object at each end. Because we are neglecting the mass of the rod, the moment of inertia of the baton about an axis through a center and perpendicular to the length is given by our moment of inertia equation. Because the system consists of 2 objects with equal masses, equidistant from the axis of rotation, r equals L for each object. So the sum is shown here. If we didn't neglect the mass of the rod, we would have to include its moment of inertia to find the total momentum of inertia of the baton. But we said earlier that I is a rotational counterpart of M, but there are some important distinctions between the two. For example, mass is an intrinsic property of the object. That doesn't change, whereas the moment of inertia of a system depends on how the mass is distributed and on the location of the axis of rotation. So in this figure, we have a uniform hoop, which can be divided into a large number of small segments that are equidistant from the center of the hoop. So you can think about that. As part of our analysis approach that we typically use. When we consider extended objects such as a sphere, a cylinder, or a cone, techniques of calculus are often required to calculate the moment of inertia. If, on the other hand, the object has a certain symmetry, we can find the moment of inertia without calculus. So, for example, let's think of a hoop rotating about an axis perpendicular to its plane and passing through its center, as shown in the figure. A bicycle tire, for example, would approximately fit into this category. To evaluate the moment of inertia of the hoop, we can still use our equation and imagine that the mass of the hoop M is divided into n small segments having masses M1, M2, M3, all the way to Mn. Then the total mass M is the sum of the individual masses. Let's rewrite our moment of inertia equation. All of these segments around the hoop are at the same distance r from the axis of rotation, so we can drop the subscripts on the distances and factor out r squared. This expression can be used for the moment of inertia of any ring-shaped objects rotating about an axis through its center and perpendicular to its plane. Note that the result is strictly valid only if the thickness of the ring is small relative to the inner radius. Okay, so now let's think a little bit more about calculations of a moment of inertia for inertial moments of inertia for extended objects. So for the moments of inertia for some other common shapes are given in this table. Our expression for the moment of inertia of a hoop can be used equally well to find the axial moment of inertia of an embroidery hoop or of a long sewer pipe. In the same way, a door turning on its hinges is described by the same moment of inertia expression for a long, thin rod rotating about an axis through its end. So in the systems approach, all masses in the system accelerate at the same rate under external forces. The masses are connected by internal forces, for example, tension, which can be regarded because they come in equal and opposite pairs. When pulleys or other rotating objects are involved, there is an additional requirement that the cables causing them to rotate must not slip, so that the tangential acceleration at the point of contact is the same as in the common acceleration of the masses in the system. Each rotating object then contributes an additional effective mass of I divided by r squared to the total mass of or inertia of the system. For simplicity, we won't consider external torques. For example, torques applied with a crank, although they can be included if the conditions aren't violated. We can then write the equation shown on the slide. For problems involving the rotational second law of motion, we need to take both translational inertia and rotational inertia into account. So in this figure, a rigid plate rotates about the z-axis with angular speed v. The kinetic energy of the particle of mass m is 1/2 mv squared. The total kinetic energy of the plate is 1/2 over 1/2 L omega squared. In topic 5, we define the kinetic energy of a particle moving through space with a speed v as a quantity of 1/2 mv squared. In a similar way, we can define the rotational kinetic energy of an object rotating about some axis with an angular speed v. Let's see how we can do this. First, let's consider the object shown in the figure, which is the shape of a thin, rigid plate rotating around some axis perpendicular to the plane. The plate consists of many small particles, each of mass m. All these particles rotate in circular paths around the axis. If r is the distance of one of the particles from the axis of rotation, the speed of that particle is v equals r omega. So of course, the total kinetic energy of the plate rotating is the sum of all kinetic energies associated with the particles. In the last step, the omega squared term is factored out because it's the same for every particle. Now the quantity in parentheses is the moment of inertia of the plate in the limit as the particles become vanishingly small. So we can write out our results as shown, where I is the moment of inertia of the plate. So in this figure, a ball starts from rest at the top of an incline and rolls to the bottom without slipping. And so a system such as a bowling ball rolling down a ramp is described by 3 types of energy: gravitational potential energy, translational kinetic energy, and rotational kinetic energy. All these forms of energy plus the potential energies of any other conservative forces must be included in our equation for the conservation of mechanical energy of an isolated system as shown, where I and F refer to the initial and final values respectively, and PE includes the potential energies of all conservative forces in a given problem. This relation is true only if we ignore dissipative forces such as friction. Otherwise, we would need a generalization of the work energy theorem. So now we'll give a synopsis of a problem solving strategy for energy methods and rotation. As usual, we want to be mapping this out. So we choose 2 points of interest, one where the necessary information is known and the other where the information is desired. And identify the conservative and non-conservative forces acting on the system being analyzed. Then we want to write our equations. If there are non-conservative forces, use a general work energy theorem. If the forces are conservative, use conservation of energy. You then substitute the general expression for the terms in the equation. You use V equals R omega to eliminate either V or omega from the equation. And then finally, you solve for the unknowns. So let's review this question here. So 2 spheres, one hollow and one solid, are rotating with the same angular speed around an axis through their centers. Both spheres have the same mass and radius. Which sphere, if either, has a higher rotational kinetic energy? And the answer is the hollow sphere. And that's because the hollow sphere has a larger moment of inertia, so it will have the higher rotational kinetic energy. KER equals 1/2 L omega squared. So let's talk about angular momentum. So in the figure, an object of mass m is rotating in a circular path under the action of a constant torque. Take a look at the figure where an object of mass m rotates in a circular path of radius r acted on by a net force. The resulting net torque on the object increases its angular speed from the value omega O to the value omega at a time interval delta t. That means we can write the equation here. Let's define the product L omega as the angular momentum of the object. Now we can write the rotational analog of Newton's second law, which states that the net torque acting on an object is equal to the time rate of change of an object's angular momentum. When the net external torque acting on a system is 0, we get delta L over delta T is 0 over delta T equals 0, which says that the time rate of change of the system's angular momentum is 0. Let Li and Lf be the angular momentum of a system at 2 different times, and suppose there is no net external torque, so that the sum of the torque is 0. That means that the initial and final angular momentum are equal, and angular momentum is said to be conserved. We now have a third conservation law to add to our list, conservation of angular momentum. We can now state that the mechanical energy, linear momentum, and angular momentum of an isolated system all remain constant. So here's an example of a skater and how they vary their moment of inertia by changing angular speed. And so just by doing some arm movement of the arms, so and other parts of one's body. So conservation of angular momentum applies to macroscopic objects such as planets and people, as well as to atoms and molecules. There are many examples of conservation of angular momentum. Consider the figure skater shown. In the first photo, the skater has pulled his arms and legs close to his body, reducing their distance from his axis of rotation, and so reducing his moment of inertia. By conservation of energy, a reduction in his moment of inertia must will increase his angular speed. coming out of the spin in the photo on the right, he needs to reduce his angular speed. So he extends his arms and his legs, again, increasing his moment of inertia and slowing his rotation. So here's a figure of the Crab Nebula in the constellation Taurus. The nebula is a remnant of the supernova seen on Earth in AD 1054. It is located some 6,300 light years away and is approximately 6 light years in diameter and is still expanding outward. A pulsar deep inside the nebula flashes 30 times per second. And so we see in figure B where the pulsar is off and C when the pulsar is on. So the figure shows a fascinating astronomical example of a conservation of angular momentum. At the end of its lifetime, a massive star uses up its fuel and collapses under the influence of gravitational forces, causing a gigantic outburst of energy called a supernova. And so the best example of a remnant like this is in the Crab Nebula, as we show in the pictures. And it shows a chaotic expanding mass of gas. In a supernova, part of the star's mass is ejected into space, where it eventually condenses into new stars and planets. Most of what is left behind typically collapses into a neutron star, an extremely dense sphere of matter with a diameter of about 10 kilometers, which is greatly reduced from the 10 to the 6 kilometer diameter of the original star, and contains a large fraction of the star's original mass. In a neutron star, pressures become so great that atomic electrons combine with protons, becoming neutrons. As the moment of inertia of the system decreases during the collapse, the star's rotational speed increases. More than 700 rapidly rotating neutron stars have been identified since they were first discovered in 1967, with periods of rotation ranging from milliseconds to several seconds. The neutron star is an amazing system, an object with a mass greater than the sun, fitting comfortably within the space of a small country and rotating so fast that the tangential speed of the surface approaches a sizable fraction of the speed of light. So very interesting and very unusual compared to what we're familiar with. Okay, let's review some questions here. And so let me just see what we've got here. Okay, we're getting close to the end of the material here. And so I'm not going to be spending too much time on these questions, but I'll just quickly give you the answer. And you can pause this recording and review them at your leisure. So a horizontal disk with momentum of inertia L1 rotates with angular speed omega1 about a vertical frictionless axis. A second horizontal disk with momentum of inertia L2 drops onto the first, initially not rotating, but starts the same but sharing the same axis as the first disk. Because their surfaces are rough, the two disks eventually reach the same angular speed omega. The ratio omega over omega1 is equal to, and the answer one is L1 over the quantity L1 plus L2. And so applying conservation of angular momentum to the system, the two disks before and after the disk is added to get the result L1 omega 1 equals L1 plus L2 quantity times omega. So if a global warming continues, it's likely that some ice from the polar caps of the Earth will melt and the water will be distributed closer to the equator. If this occurs with the length of the day, that is one rotation, and the answer is it would increase. The Earth already bulges slightly at the equator and is slightly flat in the poles. More mass moves towards the equator would essentially move the mass to a greater distance from the axis of rotation and increase the momentum of inertia. Because the conservation of angular momentum requires that L1 omega z equals a constant, an increase in the momentum of inertia would decrease the angular velocity and slow down the spinning of the Earth, thus the length of each day would increase. Okay, we've got a whole lot of slides with these assessing learning, so I'll just quickly go through these. And so the rotational inertia of the dumbbell about axis A is twice the rotational inertia about axis B. The unknown mass is, the answer is 7 kilometers. A disc with radius of 0.25 meters and mass 4 kilogram lies flat on a smooth horizontal tabletop. A string wound about the disc is pulled with force 8 Newton. What is the acceleration of the disc? And the answer is 2 meters per second squared. So going with that, but now we're going to be, what is the angular acceleration of the disc? And the angular acceleration is 1 meters per second squared. So a 100 kilogram crate is attached to a rope wrapped around the inner disc as shown. A person pulls on another rope wrapping around the outer disc with force F to lift the crate. What force F is needed to lift the crate 2 meters? And the answer is about 200 newtons. So so a person pulls on another rope wrapped around the outer disc with force F to lift the crate. What force F is needed to lift the crane? I'll just read the whole thing here. A 100 kilogram crate is attached to a rope wrapped around the inner disc as shown. A person pulls another rope wrapped around the outer disc with force F to lift the crate. What force is needed to lift the crate 2 meters? And the possible answers are 2, 3, 4, and 5. And so you can look those over a little bit. And a spool has string wrapped around its center axis and is sitting on a horizontal surface. If the string is pulled in the horizontal direction when the tangent to the top of the table, the spool will, the answer is roll to the right. If the string is pulled to the horizontal direction of the tangent to the bottom of the axis, the spool will roll to the right. So we're the same thing in both of these. And so if the string is pulled at an angle to the horizontal when drawn from the bottom of the axis, the spool will roll to the right. Okay, so here we have a coordinate system and some information to help us with these following questions. And so 2 blocks hang from strings wound around different parts of a double pulley as shown. Assuming the system is not in equilibrium, what happens to the system's potential energy when it is released from rest? And the answer is it decreases. Okay, so 2 blocks hang from a string that would around different parts of a 2 kilogram double pulley as shown. The pivot exerts a normal force F sub n supporting the double pulley. Assuming the system is not in equilibrium, which statement about F sub n is true after the system is released from rest? And the answer is 20 newtons is less than F sub n is less than 27 newtons. So we can at least bound what that is, what F sub n is. Okay, uniform rod of length L, mass M is suspended by 2 thin strings. Which of the following statement is true regarding the tension of the string? And the answer is T2 equals to 0.0 T1. So a uniform rod is hanging to a wall and held at a 30-degree angle by a thin string that is attached to the ceiling and makes a 90-degree angle to the rod. Which statements must be true? At least one of them is true and at least one of them is false. And the answer is the string tension is smaller than the rod's weight. Okay, a uniform rod of length 4L and mass M is suspended by two strings lengths L and 2L as shown. What is the tension in the string at the left of the rod? And the answer is mg divided by 2. A uniform disc with mass M and radius R sits at rest at an incline 30 degrees to the horizontal. A string is wound around the disc and attached to the top of the incline as shown. The string is parallel to the incline. What is the tension on the string? And the answer is mg divided by 4. Okay, and so in this case, I think I'm just going to skip one. So the answer for this one is mg divided by 4 up the incline. Okay, which situation has the least magnitude of angular momentum about the origin? And the answer is all have the same magnitude angular momentum. Child is standing at the rim of a rotating disc holding a rod. The disc rotates freely without friction if the rock is dropped at the instant shown. Which of the indicated paths most nearly represents the path of the rock as seen from above the disc? And the answer is number 2, path 2. Okay, a child is standing at the rim of a freely rotating disc holding a rock. The disc rotates without friction. The rock is dropped at the instant shown. As a result of dropping the rock, what happens to the angular velocity of the child and disc? And the answer is they stay the same. If a child is standing at the rim of a freely rotating disc holding a rock, the disc rotates without friction. The rock is dropped at the instant shown. Which of the following statements is true about the process of dropping the rock? And the answer is both the angular momentum and the mechanical energy are conserved. Okay. So the child throws a rock radially outward. And so then we have the same question, which of the indicated paths most nearly represents the trajectory of the rock as seen from above? And the answer is path 4. Okay. So a child is standing at the rim of a rotating disc and throws a rock radially outward at the instant shown. The disc rotates freely without friction. Which of the following statement is correct about the disc child rock system as the rock is thrown? And the answer is angular momentum is conserved, mechanical energy is conserved. So a child is standing at the rim of the rotating disc holding a rock and throws a rock in direction 2 at the instant shown. The disc rotates freely without friction. What happens to the angular speed of the disc? And the answer is it increases. An ice skater begins a spin in the middle of a large rink and then starts to spin faster by pulling his arms in. Which of the following statements is true? And the answer is kinetic energy increases, angular momentum is conserved. Two masses M1 and M2 having M1 greater than M2 are launched with the same speed in the direction A. Which mass reaches the greatest height? And the answer is both reach the same height. So two masses, M1 and M2, M1 greater than M2 are launched with the same speed in the direction B. Which mass reaches the greater length? And once again, both reach the same height. Mass M is launched from the surface of the Earth with speed V. The diagram shows 3 possible launch directions. Order them according to the maximum height the projectile will reach from greatest height to the least. And the answer is A is greater than B is greater than C. So this would be what we have in item number 6. Okay, we'll just do a couple summary charts here. And so we talked about torque. And so let F be the force acting on an object, and let R be a position vector from a chosen point O to the point of application of the force. Then the magnitude of the torque of the force F is given by the equation shown, where R is the length of the position vector, F the magnitude of the force, and theta the angle between F and R. The quantity D is called the lever arm of the force. The center of mass in motion. The torque of an object weight can be calculated using a single force applied at the object's center of gravity. The X, Y, and Z of an object's center of gravity are shown here. The center of mass and the center of gravity are exactly the same when G doesn't vary significantly over the object, which is the case for all objects in this topic. So torque and the two conditions for equilibrium. An object in mechanical equilibrium must satisfy the following two conditions. The net external forces must equal to zero, and the next external torques must be zero. These two conditions used in solving problems involving rotation in a plane result in three equations and three unknown, two from the first condition and one from the second condition on torques. These equations must be solved simultaneously. The rotational second law of motion, the moment of inertia of a group of particles, is defined as shown. If a rigid object free to rotate about a fixed axis has a net external torque acting on it, then the object undergoes an angular acceleration alpha. This equation is a rotational equivalent of the second law of motion. Problems are solved by using this torque equation together with Newton's second law and solving the resulting equations simultaneously. The relationship between A and alpha is often key in relating the translational equations to the rotational equations. Rotational kinetic energy. If a rigid object rotates about a fixed axis with angular speed v, its rotational kinetic energy is defined as shown, where L is the moment of inertia of the object around the axis of rotation. A system involving rotation is described by the three types of energy: potential energy, translational energy, and rotational kinetic energy. All these forms of energy must be included in the equation for conservation of mechanical energy for an isolated system where I and F refer to initial and final values respectively. When non-conservative forces are present, it's necessary to use a generalization of the work energy theorem. And for angular momentum, the angular momentum of a rotating object is defined as shown. Angular momentum is related to the torque in a given equation. If the net external torque acting on a system is zero, the total angular momentum of the system is constant and is said to be conserved. Solving problems usually involves substituting into the expression shown and solving for the unknowns. Okay, well, thank you very much. We're at the end of our lecture. Bye-bye.